Welcome back to the next video, everybody. Today, we're going to look at Schlesinger's representability theorem. So this theorem is used at a number of points in the construction of universal deformation rings, although the construction we will look at next chapter actually doesn't use this theorem. But nonetheless, it's important to cover. It's definitely surrounding tangential material that's very relevant to the subject at hand. Okay, so let's recall the map H from D of A cross B over C to D of A cross D of B over D of C from the Mayer-Vittorus property. That property demands that this map be bijective. Okay, so Grothendieck has this theorem. It says, let D from C lambda to sets be a covariant functor such that D of K consists of a single element, par for the course by now. Then D is pro-representable, so it's representable in the larger category C hat sub lambda, i.e. D equals D sub R, the functor that sends dr of B to maps from R to B for some coefficient ring R in C hat lambda, if and only if D has the Mayer-Vittorus property and the tangent space dtk is finite dimensional over K. Okay, so we don't really need this theorem. And the real point here is that it's actually kind of hard to use this theorem. In contrast to this theorem, Schlesinger's theorem will tactfully reduce the number of diagrams that we have to check Mayer-Vittorus on. Okay, so Grothendieck's theorem is hard to use basically because it demands that you check Mayer-Vittorus on all diagrams. So Schlesinger will say, no, you don't really have to check on all diagrams, just on some of them. Our preliminary definition here is that a map rho from A to C in C lambda is small if its kernel is a principal ideal that's annihilated by MA, the maximal ideal of A. So here's the theorem. Let D from C lambda to sets be a covariant functor such that D of K is a singleton. Then D is pro-representable if and only if the following hold. The first property is called H1, and it says that H is surjective if A to C is small, which is actually equivalent to H is surjective if the map from A to C is surjective, which I find just easier to remember. Okay. 2, so property H2 is H is bijective if A to C is the map from K bracket epsilon, the dual numbers to K. And we'll note that H2 implies TK, the tangent space property from my tangent space video a couple videos ago. So in particular, TDK is a K vector space. Okay. Property H3 is that TK holds and the K dimension of TDK is finite. So we saw that above. That's an essential condition that we've been working with for a couple videos now. And then H4, H is bijective if A to C and B to C are equal and small. Okay, so for a proof of this, you can see Schlesinger's paper on art and rings. Okay. In view of Fermat's last theorem, for us, though, it's almost less important that our functors be pro-representable than that they satisfy the tangent module hypothesis T sub A from my tangent module video, prompting the following definition. Let A be a coefficient lambda algebra, a covariant functor D from C lambda of A to sets such that D of A is a singleton is called nearly representable if it satisfies T sub A. Together with F, property F says that TDA is finite type as an A module. So it's the analog of TDK being a finite dimensional K vector space from Schlesinger's theorem. Okay. So a remark here that's very important. Most functors that we will care about will be nearly representable and will satisfy H1, 2, and 3 from Schlesinger's theorem, but they won't satisfy H4 always. But the point is, we don't really need them to satisfy H4 because functors that satisfy H1, H2, and H3 will have what's called a pro-representable hull, and we'll now briefly describe what that means. Okay, so first of all, we need the notion of a smooth morphism of covariant functors. Morphism C from D prime to D of covariant functors on C lambda, such that D prime of K and D of K are singletons as usual, is called smooth if it has the following lifting property. If you give me a surjection beta A in C lambda and an element alpha prime in D prime of A, and any lifting of alpha, which is C of alpha prime in D of A, to an element beta in D of B, well, then there better be an element beta prime in D prime of B, which is a lifting of alpha prime, such that C of B prime is B. So if we're lifting alphas, then we have to be able to lift betas compatibly, basically. Another way of saying this, though, is just that the natural map from D prime of B to D prime of A cross D of B over D of A is surjective for all surjections beta A in C lambda. Okay. Equivalently, you can request the same surjectivity property just for surjections beta A in C hat lambda. For example, if D prime to D is smooth, then D prime of B to D of B is surjective for all B in C hat lambda. Okay. The proof is just apply the lifting property to the case A equals K. Okay, so for a list of basic properties that smooth morphisms of functors satisfy, you can see Schlesinger's paper, proposition 2.5. Okay, so what's a pro-representable hull? A pro-representable hull for a functor D is a pair R epsilon, where R is a coefficient lambda algebra, and epsilon from the functor D sub R to D is a morphism of functors, where D sub R is the functor pro-represented by R, of course, as usual, such that two things hold. This map better be smooth, okay? And then the induced map of Zariski tangent spaces, TR to TD, is an isomorphism of K vector spaces, all right? Any covariant set-valued functor D on C lambda such that D of K is a singleton and which satisfies HI for I equals 1, 2, and 3 actually does possess such a pro-representable hull R epsilon. And actually, any two of these hulls of D are isomorphic, non-canonically usually. And again, you can see Schlesinger's paper for more information about this. Okay, so we will go on and continue looking at this pro-representability stuff next time. So I'll see you then, and thanks for watching.